Hi, hello everyone. My name is Kuba, and I'm a software engineer on the Golem project. Thanks for joining this workshop session. Today I'm going to show you how to build an app on top of the Golem network, your own app basically, so that you can take advantage of all the computing power it provides. But before going into the workshop section itself, just to make sure that we're all on the same page, I'm going to quickly introduce you to the Golem project as such. So what is Golem? So Golem is a decentralized network of nodes which you can use to either request tasks, or you can start your own node and become one of the providers that we call them, to receive tasks from other people and lend your computing power to them. So it's a decentralized marketplace basically. It's all open source, and as it is decentralized, there is no like central authority. It is censorship resistant basically, and all of the payments that happen for those tasks, they happen over the Ethereum network using layer 2 payments. Right. So, and since we are focusing on actually writing applications, why would you want to use Golem in the first place? Well, there is a couple of good reasons. One is the fact that it essentially democratizes access to computing power. So it is much cheaper to use Golem for some expensive tasks rather than paying some centralized services such as Amazon Web Services or your other usual suspects in this case. It's using right now with the new implementation, which we call Yagna internally. It's using an ERC20 token called GLM. So it is, and also it's using ZK Sync for the transactions. So it's very fast. It's very convenient for you to make those payments. And yeah, there is freedom for you as a developer, which is also a cool thing. All right. Now, so what is a Golem application exactly? So on this diagram, you can see like the two sides of this marketplace. On the left, there is the requester side, and on the right, there is the provider side. So the requester actually comes with a task that they want to get computed, and it is the responsibility of this application to determine how this task or how the data for this task can be split into multiple chunks, and like how exactly is the computation going to happen. So the requester app should provide the Docker containers running inside the providers with the data and the commands that they should do. And in turn, the providers will send back the results, basically. And it's up to the requester to merge them. So this is exactly what we will be doing today during the workshop. So let's see the agenda for it. So first of all, we're going to set you up with a Golem node with the Yagna implementation specifically. Then we'll see how you can create your own Docker image that will be run by the providers to execute your task. Then we'll see the requester application itself and how we can use a high-level Python API to achieve our goal. And finally, we're going to run this application on the network itself. Right. Before I continue, I'm going to send you some links that you can check out probably after the presentation. But there is a curated list of different Golem applications that have been created so far, so you can check these out right here. And oh, sorry, come on, sorry. Right, so yeah, so this is let me jump back to it. So you can check this out. We also have bounties and other challenges that you can take for creating different kinds of applications on top of Golem. So you should definitely go and see if there's anything that you think you could tackle. Right. So yeah, let's get to it then. Here we have a couple of contact links just in case. If there are any technical problems during this workshop, it's possible that I will not be able to resolve all of them. So if there is anyone left with something that's not working, or you have some additional questions, you can just head over to our Discord, for example. Right. So yeah, as I said, first thing we're going to do is installing a Yagna node on your machines. So I sent you a link to our handbook, to our documentation. I'm going to open it here as well. Right. So here is my browser, and the link should send you to a section which is called running the Yagna daemon. So this is the one that we're interested in. Okay, so for Unix-based systems, so if you're running Linux, Mac OS, you should be able to use our installer just like so. So there is a curl command here which you can run, and this will basically get you up and running with the latest release of Yagna. If you're running a Windows machine, unfortunately, we do not have such an installer for Windows yet. So you will have to follow the manual installation, which is described here below. Okay, so let me let me follow along. So I'm going to open my terminal now and paste in this curl. It asks me for root privileges to user bin, so let's do this. Okay, everything seems to be good. You can verify your installation by running Yagna -- version, which is also in the docs. Right, so let me paste it in here. So this is the version I'm running. It's build number 113. The version is 6.0. And we need to do the same thing for GFTP, which gets installed alongside Yagna and is used for transferring files between the nodes in the network. And this should essentially give you the same result. So it should be same build number and same version number. Cool. So this is how you install the Yagna daemon. Before I proceed, there is one important thing. If you've already, if you had Yagna installed previously on your machine, please make sure that you do not have any mainnet ETH or GLM stored on your account. This is because what I'm going to do in this next step is I'm going to just remove the working directory for Yagna, which is, well, destructive, just to make sure that we're running the latest version. So if you had something before, it's best to just copy this directory somewhere else, and only then either remove it or move it somewhere else. So just you can read through this section carefully and make sure that you're not losing anything. Right, so yeah, I'm pretty sure that I'm not losing anything here. So let me just nuke it. Cool. And the next step here is actually running the daemon itself. So there is Yagna service run is the command that we're interested in. And this is going to start the server, start a node on your machine. I've opened a separate terminal window for this, as we want to keep this running throughout the workshop, because we'll need it later on to actually request our tasks. It is the sort of your gateway to the Golem network. So yeah, let me run it. We're going to see a bunch of logs, and the log that we were interested in is starting some number of workers, and then there is the Actix web service. This is what we're interested in. If you see this, then it means that we're all good, that the daemon is running correctly. Right, so once we have this running, the next step is to generate yourself an app key. This is a one-time thing. By default, Yagna does not create any application keys for you, so you need to do it by yourself. And this app key is basically sort of an identification for your application. So I'm going to copy again the command from the manual here, and create a key that will be called requester. So this is the name of the key. So let me open. Oh, we get a bunch of warnings about some offers expired. There's nothing to worry about. Right. So I'm pasting in the command here, and yeah. So the key is created. You can verify this by listing those keys. Here below, you get Yagna app key list command. And yeah, we see that the key matches the one that was printed up here. So this is the key that we're going to use later on for requesting our tasks, for like using our application. Okay. Now, I mentioned those GLM tokens that we'll be using for actually making payments. What we're running right now is all happening on the testnet. So this is the Ethereum Ringkeepy chain, which does not use real GLM. So you're not paying real money for this, and so we can simply use what is called a faucet to request some funds, so that we can run an application that would otherwise require us to pay, basically. So to request those funds, we call Yagna payment fund. So going back to my terminal here, and this, depending on the load on the faucet, this may take a couple of seconds or maybe half a minute. You will see some logs in the Yagna daemon terminal. So you can just leave this running and wait for the commands to finish. If it finishes with a failure, you can just retry it. This is sort of expected, especially when we're having a bit of a increased load during this session. Okay. In my case, I've received some funds. So there is a message here, as well as a log in the Yagna itself. You can just leave this running. You can leave this running for now if it's taking some more time for you. And the last thing that we'll need is initializing our node as a requester, so that it is able to make payments, to be a sender of the tokens. But this needs to happen once we've received the funds from the faucet. I'm going to do this now, but as I said, if you're waiting, you can just rerun this step later on. Nothing will break, nothing bad will happen. Okay. So yeah, so this is all that we needed to do to get a working Yagna node on our machines. Now that we have this, the next step here is to actually start working on our application. And during today's session, I'm going to show you an example written in Python. And the example, well, let me find you the link first, shall we? Here it is. So yeah, I'll send you the GitHub link to it. And the example is a very simple dictionary attack on some pre-computed hash, a SHA-256 hash. So our application is going to having some dictionary. We have two flavors here. One is like a short list of words. So having a dictionary that is like a single word per line. It's going to split this dictionary into multiple parts and send these parts to providers and have them try matching those words against some hash that we've included here. So yeah, so that's the whole idea. Okay. Once you're here on the GitHub repo page, there is a section called Hello Decentralization Workshop right here. And this section tells you that if you want to follow along the live coding, because I will be doing live coding in a second, you should switch to a Git branch that is called Workshop. So I'm going to do this right now. So in my terminal, I'm leaving the Yagna thingies running. I'm going to switch back where we were previously. And yeah, I already have the repo cloned. And now, well, I'm already on the branch, but just to make sure, say git checkout workshop. So here it is. And yeah, so this is the first step for us to start working on it. Now, if you have the repo cloned already, you will want to set up your Python environment for it. And to do so, there is an installation section down here, again in the repo page. And well, the installation is basically creating your own virtual environment for Python, and then installing the requirements from a list that's included in the repo. So yeah, so first off, you should probably check the Python version that you have on your system. And well, if you choose to run it with that Python, it's fine, but I would recommend that you actually create a virtual environment for it so that you don't install all of these dependencies to your system. So just for a moment, let me open up another window. And here we have Python 3 / version. In my case, the system one is 3.6. And to create a virtual environment, you can either use any tool which you like. There's a couple of them for Python, unfortunately. But the instructions show you the most basic way of doing so. In my case, I should already have one ready. So let me just check the version here. Yeah, so this is different from the system version. The docs here say 3.7 plus, but you can run on 3.6 too. That's fine. Okay, so if you have your Python environment ready, then the last setup step that we need to do is installing the dependencies. So we call pip install -r requirements txt, hit return. We should see a bunch of things installing. Obviously, we only have two things in our requirements file. One is the high-level Python API, this one, And the other one is a tool that we use for building VM images for Golem. So we'll see why we need this in a second. Okay, I'm going to give you a moment to install those things, and then I'm going to move on to actually writing this example. All good so far? Like no one's stuck, no questions? Lighten up. Okay. Fine. Okay. Let's move on then. So we have the environment ready to go. Now, if you take a look at this repo, we have two Python files, requester.py and worker.py. We have the requirements file that we've just seen, and we have a Docker file. Other than this, there's also the data directory that contains all of those dictionaries and hashes that we'll be working on. But yeah, that's pretty much it. So I'm going to switch over to my editor window now and start off with this worker.py file. Yeah, here it is. So there is a comment at the top of this file telling you that well, this script is actually the one that will be executed on the provider's VMs. So this means that this is the place which will actually be responsible for doing the work that we want to get done. So in our case, that is cracking the hash. So there is I've prepared sort of a template here that includes those three file paths for us, and these file paths are going to be inside the VM already. But once we see the Docker file, this will probably be easier to understand. Maybe I can actually just open the Docker file alongside here. So yeah, so on the right we have the Docker file from which we build the VM, the machine that will be running our code. And as you can see, it includes two volumes. One is /golem/input, and the other one is /golem/output. And you can see the same things here in those paths. So the image is expecting to have those two directories present, and our script is assuming that input is going to contain both a list of words and the hash to crack. And it's also has a predetermined path into which it's going to write the result, the output of the computation. So if it finds a matching word, then this is where it's going to be output. So yeah, so this is why we have those paths over here. Okay, let me close. Well, the Docker file is pretty straightforward. Like, apart from the volume, you have a copy instruction which copies this script, this worker.py file, into the machine under this path. So Golem entry point, and finally it sets the working directory to this Golem entry point directory. So yeah, that's all that the Docker file is doing at this point. We'll see in a moment how we build it and how we can use it with our application. Okay, so coming back to the left side of things, maybe let me just focus on it. I've left out the actual implementation for this cracker, but otherwise we have these three stages. So One is loading the file with the hash so that we have it as a string here in this program. Then we have loading the words themselves as a list of strings again. All of these files are JSON files. This is like, we assume that we communicate using JSON. And finally, there is the result path, so where we actually writing the result. Okay, so let's add the cracking implementation first. So we have a list of words, right? So we probably want to go over each and one of them and calculate the SHA of this word and compare it to the target one. So we're going to start off with a for loop over those words, like so. And we want to, since we are calculating the hash, we need to convert this line, this single word in the line, to bytes, so that it can be passed into the hash function. So let's call this one line bytes. And let's see. So in Python, there is this built-in function called bytes, which takes a string and its encoding and returns like the byte form of this string. So sounds good. Sounds like that's what we need. So the string in this case is the line. We're going to call strip on it to remove any trailing or leading white spaces, since in our file we have new lines at the end. And the encoding is actually stored as a sort of a constant here. So you can see it here. So it's UTF-8. Right, so this is the bytes representation of our line. Now for the hash function, we need to import it. So let's see, from hashlib import SHA-256, right? So this is, I think this is the one that we need. Cool. Now let's see. Let's calculate the hash now. So we have line hash equals SHA-256, and this takes the bytes. So this is called line bytes, and this one returns bytes itself as well. So to convert it to something human readable, or to have a string representation of it, we call the function hex digest on it. Right. So this variable now is going to store our line's hash. Now we want to compare it with the target one, so the one that we've received from our requester. And well, if it matches, then we store it as the result. So we store the word basically as our result, which is here, this one. And at this point, we can break this loop, right? Because we found the result. We're pretty sure that we're not going to find another matching hash, so we don't have to go through the whole thing. Right. So yeah, if the result is stored, then at this point here, the last thing that the script does is saves it as a JSON to a file. So that's what we wanted. Okay, this sounds good. Sounds like it should work. We can verify this by changing those paths temporarily to something that we know. Let's see, we have this data directory. So let me see what we have. It contains these 4 files. So yeah, so let's just copy over one of those. And we can, this is the hash path. So we say data / hash short. Words is words short, and then finally the result. Well, we can just say output.json. So we can run this locally on our machine on this short list of words to see if it's actually working as expected. So let's do this. We do worker py and just run it. Oh, sorry, something's wrong. Okay, right. Sorry, the list of words is supposed to be a JSON because we are sending in a JSON, and the way we store it here is actually a plain list of words. So okay, so let me just skip this then. We'll see this working once we send this over as a JSON. Okay, cool. So next up, I've shown you the Docker file that we can use to build this image. So very quickly, I'll just show you how we can obtain a Golem VM image from it. So first off, we need to build this Docker image. So assuming that you have Docker installed, again, this is an optional step. We don't really need to do it at this point. So assuming you have Docker installed, let me find this. There is Docker build. So we need this. Docker build. The dot indicates this current directory, which contains a Docker file. And this -t means that we tag this image with the name #cracker. Okay, so that seems fine. We see the same instructions that we've seen in the file itself. So that looks good. And we've successfully built an image. Now, the Golem VMs don't act on Docker images directly. Instead, they rely on a internal format, which is called the GVM, or the Golem virtual machine. And if you remember from the requirements that I've shown you at the beginning, there is this package called GVM kit. And this is exactly the thing that we need to convert a Docker image into this GVM image. So to actually convert it, all we need to do is say GVM kit-build and specify the name of this Docker image that we just built. So that would be #cracker, and the tag here is latest. So if I call this, you should see this fancy output, lots of things happening. But the end result is a single file that will be created in the current directory. So you can see this guy. So docker hash blah 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 .gvmi. Yeah, so that's the thing. That's the packed Golem VM image that will be sent to the providers. Now, the last thing, if you want to provide it to other nodes, would be to upload this to the Golem image repo. So the providers do not, they look for those images at a specified location. And so in order for you to share this one, you need to upload it there first. So this GVM kit instruction I've shown you has this flag called push, and that results in this image being sent over to that repo of images. So yeah, this takes a couple of seconds since this is a network upload. And once it's finished, we should see this, the hash link. And I will show you in a moment where this will be useful. But this is essentially the identifier of our image on the repo. So we need to tell the providers, hey, go fetch this one from the repo so we can do some computations using this image. So yeah, so this is how you would build your own custom Docker image. Now, let's move on to the requester application itself. And yeah, I'm going to come back to this one in a moment. So back to my editor, and I'm switching over to requester.py. So this is the other Python file that we have. And again, this file is also like partially ready. So it has some boilerplate, like for example, the CLI arguments that we can pass to it. We have some paths that we'll need, and we have some functions defined. So the requester application is actually going to perform like three steps. The first step is preparing the data, which will be handled by this function. And preparing the data means splitting it into chunks, into tasks that can be sent over to providers to compute this task. So in our case, if we take a look at, let me switch back to it. If we take a look at, for example, our words example, so this dictionary, we have this dictionary, right? So this data thing right here, what it should do is, given some chunk size, which we could potentially change to, I don't know, 2, for example, it would split this dictionary into task sizes of 2 lines, 2 words. So this would result in one task having the words "this is," the second task being just A, and the last one having like the reminder. So in this case, that would be just test. In the case of like our actual problem, the dictionary is much larger. So this chunk size is set to this value, to like 100,000 of lines. So yeah, so this is the first step. We prepare the data. Once we have it, for each of these tasks that we've created, we're going to define what commands need to happen so that the provider actually executes our task. So that's the second part, and I'll go over this in more detail in a moment. And the last thing is actually using the high-level Python API that we've included in the requirements, which is called YAP API, to communicate with our Yagna node that we've started at the beginning, and to actually perform this computation that we want. So yeah, I hope this is somewhat clear right now. There is a comment at the top of this file again, sort of explaining these stages. And yeah, so what I'm going to do now is I'm going to implement all of those stages. So starting with the data splitting part, and then going to the steps part, and then finally like combining it all together to get a working application. Right. So yeah, let's start with the data. So again, we know that what we receive here is a path to a file that contains the words. We've seen it before. We know that this is single word per line with line breaks. And we also know that we want to split this file into tasks or chunks, which will have the size of 100,000 words each. So yeah, so how do we do this? Well, we need to open this file. that's the usual part. And once we have it open, we're going to iterate over the lines and collect chunks as we go. Since we don't know how big this file is, and it can possibly exceed the size of our machine's memory. We do not want to load the whole file, at once. So that's the safer approach, let's call it. Okay, so let me open this file. So in Python we have this with, which is a context manager, meaning that this open call returns us a file descriptor. We can assign it a name. In this case, we can call it just f. And this with block makes sure that this file descriptor gets closed as soon as we're done working with it. So we don't need to do this manually. So okay, within this block, the name f is going to represent an open file, so we can already read lines, read data from it, basically. Okay, so I mentioned that we'll be building chunks as we go, so we probably need some variable that will be storing those. So let's call it chunk. That's creative. And having this file open, again, Python allows us to iterate over those lines like this. So this means that for each line in the file f, we can do something. So sorry, no file path in the open call, someone asked. So no, we don't need the file path actually, because we're getting the file from the outside. This is a path variable type, so it's already representing a path to some file. So we don't need to specify it. Cool. So yeah, so coming back, we have those. We iterate over those lines. So in this for loop, the variable line is going to represent each and every line in the file. And since we want to just build chunks of some size, the first thing we do is just add this line to our chunk. So we can say chunk dot append, and we pass in this line. And yeah, as we've seen previously, it's probably a good idea to call the method strip on this line to make sure that we don't end up with some extra characters, because that will result in a completely different hash being computed. Okay, so yeah, we add the line to our chunk. Now we want to check whether the chunk is already of the size that we want. So this will give us the length of our chunk, and this is O1 complexity. It doesn't need to go through the whole list. And we compare it to chunk size, so the thing that we get from as a parameter here. Okay, so if this matches, we want to create a task with this chunk and return it somehow. So since this function returns an iterator type, this means that we simply want to call yield on this, meaning that at this point the iterator will return something. And in our case, this something is a task object, which I'll explain in a second. And the constructor for it takes a single argument, which is data. And in our case, this data should be the chunk, basically. This task gets imported from the Python API here, and it simply represents like a single unit of computation that we're doing by the providers. So this is what kind of binds between this piece of data, this piece of the dictionary, and the provider that will be calculating it. If you remember the worker script that we've seen, this is what is going to end up as one of the inputs, so as the words.json file. Okay, so this is how we return those tasks. Some last things that we need to do is we need to clean our chunk variable at this point, since we'll be adding some new stuff to it. And once the for loop is finished, we want to make sure that we return also this shorter chunk, this end of the dictionary. So, for example, if you have a dictionary of 300,000 words, we would have three full chunks and nothing left. But if we had a dictionary of 300,005, that we also need to take care of the last 5 words in it. So what we need to do is we need to check if there is anything in this variable. And if there is, we repeat what we did previously. So simply yield the task, like so. Okay, cool. So this should be everything for our data function. Again, we can try testing it to see if we didn't get anything wrong at this point. So I'm going to jump down to the main section here, and after parsing the CLI arguments, I'm simply going to call for chunk in data, and the words file would be taken from the arguments. So like this, and the chunk size, we can say something smaller. We can print each of the chunks. So this is how I'm going to check whether this works. The args.words is taken from the CLI arguments down here, like this one. So by default, it gives you the full size dictionary. We can change this in a second. So yeah, let's see. So requester by, and we say words will be data, the short one. Yeah, we can see. Okay, let's run it. Oh, cool. Here we go. So this returned 3 tasks, and they seem to be split correctly. So we have 2 of them having 2 words as we requested, and the last one is a single one. Okay, let me remove this test code from our main function. Okay, so data is finished. Now off to the steps function, which so at this point, okay, maybe let me start with just explaining the parameters that we're receiving here. So we have something called the work context, and we have an iterator of tasks. These tasks are the same type that we've returned from data. So well, we can assume that this will be the same ones that we've created. And this work context is this kind of a special object which allows us to queue up the commands that we would like to execute on the provider. So a single context object, a single context object actually represents a single provider that we are talking to, basically. So we have a single context, and one provider can receive multiple tasks. So we can give them more than one at this point. If you'd like to, well, so this work context provides you with a couple of different methods. So for example, you can use it to send a file to the provider. You can use it to run a script. And finally, you can use it to download some results. You can see the full full reference, full documentation for it in the handbook, in the API docs again. Okay, so in the case of our program, what we need to do, one is we need to send over the dictionary and the target hash. So that's the first thing that we want to do so that the provider has the necessary data. And then two is we want to run the script that's in worker py, and that we've already included in the Docker image that we're sending to the providers. And then finally, after running the script, we want to get the results, right? So we want to download the results from the provider. Okay. So yeah. So how do we do this? This, as I've mentioned, this context allows us to queue up or to perform those things. So let's see, context dot, and yeah, we see a number of things that we can do. And there is this send file method here, which has the source path as the first argument and destination one as the second. So this sounds like what we want, right? We want to send whatever we passed in as the arguments to this program to our provider. So the one file that is not going to change between the providers is the hash, right? Is the target hash, because this is always the same one. The words list will be different, but the hash will be always the same. So we can start with sending the hash, and it is stored here. So again, args is the object that stores our arguments, and as you can see, there is one argument that's called simply hash, and that is the path here. So yeah, so this is where we take it from, and well, where do we put it? The destination path needs to be aware of the paths on the provider VM. So if we, I'm going to open the worker py file here on the side to show you those three paths. So these are the paths on the provider within the VM. So the one that we're interested in is this one. It's the hash path. So instead of copying it to this requester file, we can just as well import it like in a Python way, and then reuse the same variable, because we have this file locally. So yeah, let's do this now. I'm going to jump to our imports, and we already have it here imported, right? Because it's a local file. It's this one. So okay, so we can just use it. So we say worker dot hash path. Okay, so this one makes sure that our provider receives the target hash. Now, everything else that happens in this function should happen for each individual task. So that means that, as I've said, the hash itself doesn't change, but the list of words is going to change. And that means that it will be dependent on the tasks that we receive. So at this point, we will need to add a loop that goes over those tasks and does something for each of those. So let me add it, and I'll explain this in a bit more detail in a second. Right, so this tasks iterator is asynchronous, as you can see, And that is because we don't really know how many tasks a provider is going to receive. And this function sort of provides the mapping between a provider and the tasks that they compute. So this iterator may not return, may return just one task, it may return 3 of them. It all depends on what happens during the computation. So this is why it's asynchronous, because we're not really sure what's going to happen. And then it also needs to talk to the API internals, but more on this later on. All we need to know at this point is for each task that we receive from this iterator, we need to perform the next steps. So that means we need to send it the appropriate arguments. We need to execute the script and finally get the results, because for each different task we may get different results, right? So this needs to go into this loop. Okay, so let's start with sending the input. So sending the words themselves. So again, we say context, and this context has, next to send file, it also has this send JSON method. And in send JSON, we first tell what provider path this should go, and afterwards we specify the data. Okay, so the provider path is simple because we take it from the worker again, and this should be the words path in this case. And the data, well, where do we take this data from? Well, the data is bound to the task as we've seen it previously. So as we've done at this point, the data is stored within this task object. We do this here when we create those objects. So that means that if we want to obtain or get this data from this task, we need to do the reverse. So we basically need to say task.data, right? Because we get task objects here. So we can reference this data field. Yeah, so this is send JSON, and it's going to take care of actually serializing this to a JSON and then sending it over to our provider. Cool. I think we're done with sending the inputs. We have both the hash and the list of words. The next thing that we need to do is run the script, like we said. So to run the script, again, we say context, and there is a method called run, simply. And this method accepts the command as its first argument. So there's an example like /my directory run.sh. And then it can optionally also accept some arguments and the environment for it. So let's use it. In our case, what will be the path? Well, we've already seen this. So the path is here in the Docker file. This is where we copy our worker script within the Docker file. So this is /golem /entry point and the name of this script. So that's what we need to call on the provider. Let me come back to requester. And actually, this path is already added here for your convenience, so that we don't need to write this manually. So it's called entry point path. So let's just copy this and come back to where we left off. So here. So we want to run whatever is stored under this entry point path. I'm converting this to a string, since entry point path itself is is of type path. So just to make sure that we pass it as a string. Okay, we don't need any arguments to it because like everything is already specified in worker py in the script itself. So what's left? What's left is getting the results, right? So yeah, so as you can already probably guess, we're going to use the context for it again and say download file. And this one has the remote path first and then the local path afterwards. So the remote path is defined in our worker file, and it's called result path. And the destination, well, we don't know yet, right? This is our local file system. We could specify a single file, but this could end up overwriting each other's results, right? Because we could have one task finishing and actually having a result, and then another one coming in and just overwriting whatever was stored in that file. So we probably want to have, at least temporarily, we want to have separate files for this. So this temporary part is sort of important, because what I'm going to do is I'm going to create a temp file and write this result to this temp file. And once it's there, pass it on to like the later stages of our program. So yeah, so let me, to get a temp file in Python, we can use a library that is called, well, temp file. So from temp file, we import something that's called a named temporary file. So that's what I'm going to use. And yeah, let's create it beforehand. So we have a variable called output file, and it is a named temporary one. And yeah, and we're going to pass it to here, to download file. So we say output file dot name. The name here is actually the path to this file, because this method is expecting us to provide it with a string. So that's what we need to do. Okay, so yeah, so after this step, we should have the result downloaded to some named temporary file. So yeah, so that's all that we've sort of anticipated would go here. Now the last part is this context object is actually only queuing up those commands that we've specified. The execution happens once we call something called context commit. It's here. So this says creates a sequence of commands to be sent to the provider. And this call is actually needs to be asynchronous. I mean, it needs to yield at this point, so that the executor, which we'll see in a moment, which is the main object from our Python API, can actually take those commands and send them or queue them up and send them to the appropriate node. So yeah, so this is the part where the execution actually happens. So after this yield, we already have a task that's finished. So at this point, task is finished, either successfully or not, because it didn't have to go, as planned. In the case of this demo, I'm not going to be handling the failures, but we could, for example, say that we could reject the task as a requester at this point, and this would mean that it gets like re-added to our queue here, so to those tasks. So that means that it will be recomputed by someone. So yeah, so if we can reject it, we can also accept it, right? We can accept this task. So we can say task and accept result is the method that we were interested in here. We could also say reject result. And this one is actually has two meanings. One is that it says that this is fine, this is accepted. We could verify this result if we need to, but for the purpose of this example, I'm not going to do that. And the other thing is we're actually setting the result for this task, so that later on we can retrieve it as finished. And this happens through a parameter that receives. This parameter is called result. And yeah, what needs to happen? Well, we had this output file, so we need to load it. As we've seen previously, all of the communication is in JSON. So the output file that we've downloaded is also a JSON. So in order to parse it, we need to use JSON, right? So in Python there is JSON.load, and we say output file like this. I believe that JSON is not imported at this point, so yeah, I will need to add it. So we just say like that, and let's come back. Okay, so yeah, so this what this achieves is that our task will have some result attached to it, and yeah, at this point we're pretty much done. We've sent the inputs, we've downloaded the results, and we've assigned it to our task. The last thing that we can do is we can close this file that we created previously, just for to be tidy. Yeah, but otherwise this is all that needs to happen for a provider. Okay, cool. So we have two of the three parts done. So we have this steps function. We have the data that we did a while ago. And now the last part of this whole exercise is to combine this together, use those two functions to actually communicate with our Yagna node and get the tasks running. So let's see how this happens. There is this function called main, which is asynchronous because, well, the Python API the Python API is asynchronous, so it needs to happen. It needs to happen in an event loop. So that's what's here. And this function main gets created as a task and queued. Well, yeah, okay. This is some boilerplate. We don't really need to focus on it too much. The important part is in main we want to create this executor object that we'll see in a moment, and it will use the functions that we just created to execute our task, to execute our application. And here, as the first step, you can see this this package variable being created. This package variable specifies what image we're going to be using. So if you remember, when we built the VM image. I'm going to jump to our console. When we built the VM image, we've received some hash after uploading it to the repo. So this is the place where we can specify this hash, where we can paste it in. So yeah, so let's do it. Let's use the hash of the image that we've created and update it here. Okay. In addition to that, we can also specify some requirements that we want. For example, how much memory we think that is the minimum to perform our task, how much storage we're going to need, etc. But the most important part here is this image hash, so that the providers know what image they will be working with, basically. Okay, so yeah, let's finish this up. So we have this this executor executor class, which is well, we first need to import it from the Python API. Let me get there. So this is YAP API, and this is called executor. Yep. Okay. Okay, we're back here. So to create it, well, we simply go like this. This is a constructor, and the constructor for this class takes a bunch of arguments. It most importantly, it accepts the package. It will be the object that we've just seen was created here in the main function. And otherwise, there's a number of things that we can use to customize it. So we can specify the budget for a network. We can specify the subnet that we want to run it in, and so on. There's a bunch of things that we can do at this point. But for the sake of this example, I'm going to go with the minimal subset. So yeah, so the package is important. Max workers we don't really care about. The budget we do need to specify. As you can see, it doesn't have a default value, but yeah, this is testnet, so we don't really care. The budget can be arbitrary. Next, so there is the subnet tag, which I'll come back to in a moment. There is a timeout for the whole task, so that it doesn't get stuck indefinitely. And this timeout is actually expressed as a time delta object, something that in Python can be used to say how long something is going to take. So I think this is already imported here. Yes, there is this thing called task timeout, this constant. So yeah, let me copy it, and we can use it. We can use it here. So this will be our timeout. The subnet tag. This is the name of the subnetwork that we want to compute our tasks on. This is kind of a technicality. In our case, we do have a preferred subnet at this point, and this is passed in as a CLI argument. So let me show you. Yeah, this is here. So there is this argument subnet, and it has some default value. This one. So we can just use this as the subnet, as this argument. So we say args.subnet. Right, and yeah, there is one more thing, but I'll come back to it. It's only related to logging of the API stuff, so I'm not going to cover it right now. And yeah, so this is the executor. And now, how do we run it? To run it, we say something like executor.submit. And as you can see, this accepts two functions. One is worker, the other one is data. And in our case, these will be the functions that we've prepared some time ago. So the first one is steps, and the data needs to be an iterator. So we need to call our data function with the list of words that we would like to use. So I'm going to go with data, and the file will be args.words. So this is also coming from the outside. So this is submit, but this needs to be, again, this needs to be asynchronous, right? Because this submit function will be returning, like gradually returning tasks which have been finished, which have been successfully computed. So this is kind of, you know, linked to what we've been doing here. So every task that we accept in this steps function is going to end up in return from this submit. So yeah, so we then need to make a loop over those tasks, and this loop will need to be asynchronous for this reason. Like so. This is empty for now. And one last technicality is that executor needs to also has some context manager inside of it that we need to. So just like opening a file using this with keyword in Python, executor has the same, but again, this is going to be async because it's again, it's an asynchronous thing. You can read up some more on those, like on the reasons for this in the docs. I'm going to not be going into it right now. Okay, so in this for loop body, we'll be getting finished tasks. So that means that at this point we can already check the results and see if we get something. And if we do, then yeah, great. Then we're done. We can finish the whole thing. So that means that we can say something like this. So if a task has a result which is like not empty, not null, not an empty string, then we can store it, or we can just simply print it out. So let's go with just, you know, printing this out to the console. So we say print, and let's do like a format string result like this. And yeah, and since we already have something, we can return early, right? We can just break from this loop, because we don't need to be scheduling more tasks. And yeah, this is basically the main function. This is all that we need to do. So we create this executor object, and then we submit what we've prepared for it. So we have those two functions. Now, before we run it, to make sure that you see all the logs that you should see, there is this thing, this function call, which is imported from the Python API, which is enable the default logger. But there is an object that we need to pass into the executor so that we get a summary of the task that we've run. So this is optional, but I'm going to include this so that the logs that we see are more readable for you. So let me just quickly import those things. So we're going to need a log summary, and we're going to need log event. This is, as I said, this is optional. Let me just add this real quick. What was it? Log summary. Okay. Yeah. Format it so that it's a bit more readable. All right. Cool. So yeah, let's try running this then. Our program has these 3 arguments, but they are all optional. So by default, we're going to use this file for the hash and this one for the dictionary. And then the subnet that we use will be this one, the Golem subnet. So we don't really need to specify anything on our own. All we need to do is just call requester.py. So yeah, back to the terminal. And now, if you remember, we did run a Yagna node at the very beginning of this whole thing, which is here. Yeah, don't bother with those databases log thingies. And this Yagna node has some application key that we generated. So this application key, I think I've already, I've mentioned it back then, is what's going to sort of identify our app with this node, with our local node. So we want to specify it using a environment variable like this one, Yagna underscore app key, so that our requester application knows what key it's supposed to use for requesting this task.
Okay, really quick. You have around 3-4 minutes left. Okay.
Yeah, cool. So yeah. So this is at this point I'm going to run the program, and you can see you'll be able to see the output from the networks of stuff happening at this point. So we've received some proposals, and we've sent a task to some provider right here. So task sent to a provider with some data. This has happened a couple of times. And now, yeah, a number of providers are calculating this. And once we get a result, the program should let us know, right? Because we did add a print at this point. So it seems like we haven't found it yet because we've sent a couple of tasks, but no one is responding. Okay, there we go. So this is the summary of our cost and who computed what. And this is the result that we've printed. So this the hash that we were trying to find actually matches the word decentralizationist. Right. So yeah. So this is the log that we've added. So we can just check this. Found. Yeah. So this is where it's happening. Okay. So yeah, that's all. I know it's been quite a sprint. So yeah, thank you for following along, and yeah, if you have any follow-up questions, like technical worker questions, you got stuck on something, you can reach out on our Discord. So yeah, let me just show this again. You can also take a look at the docs at handbook.golem.network to learn some more about what I was going through. And yeah, finally, everything is open source and available on our GitHub. Cool. Okay. So yeah, thank you.
Thank you. Thank you so much.